In this video, we're going to look at the seventh and final question of the A-Level 2022 Further Statistics paper. It's actually a question that the examiner said is the most difficult question on the paper, with just over 10% of the candidates making no progress. It should be the fact that this is a final question in the paper and therefore not many people got to it. But let's take a look together and see whether we're able to get all the marks. This question is testing us on two concepts. The first one, which should be very, very familiar to you, is the central limit theorem. The second one, which could be quite tricky to some of us, is to do with type 2 error. And I suspect that's the topic that most people tripped up on. Let's take a look at the question. It says a machine fills bags with flour. The weight of flour delivered by the machine into a bag, X grams, is normally distributed with mean mu grams and standard deviation of 30 grams. To check if there's any change to the mean weight of flour delivered by the machine into each bag, Olaf takes a random sample of 10 bags. The weight of flour X grams in each bag is recorded as the mean of X, 1020. So the mean of the 10 bags are recorded as 1020. We're given the mean mu and the standard deviation 30 grams. Again, before we do anything further, whenever we see a question talking about a distribution of a mean in a number of different samples, we should know that we need to use the central limit theorem. So let's do part A together. Part A asks us to test at a 5% level of significance two hypotheses, H0 being mu equals 1,000, against H1, the alternative hypothesis of mu doesn't equal to 1,000. Another thing for us to pay attention to when we look at two hypotheses here, H0 and H1, we should be able to immediately say whether it's a one-tail or two-tail test. Now, H1 says mu doesn't equal 1,000, so therefore we can write down this is a two-tail test because we are testing whether whether mu could be higher than or lower than 1,000. So it's a two-tail test. This is what we can write down. So even if we're testing the 5% level of significance, we will be looking at 2.5% either side. So this is a normal distribution, 2.5% critical region either side. Now let's write down a few other things we know about central limit theorem. Central limit theorem tells us that, let me put that in green, X bar, which is the mean of the distribution, follows a normal distribution with mean mu. Mu is the mean of the underlying distribution and variance of sigma squared over n, n being the number of samples. What else do we know? We know that the standard deviation is 30 grams. Instead of writing 900, I'm going to write 30 squared because then I know which is the standard deviation and which is the variance. N, we know there are 10 bags, so therefore n is 10. Now, under H0, mu is 1,000 under H0. Now I'm asked to test at a 5% level of significance the null hypothesis, given X bar equals 1020. So I don't know where X bar is. So now I'm going to draw on my diagram. So under H0, my mean would be 1,000. I want to see whether 1020 is in the critical region or not. So 1020, I'm going to draw in purple. 1020, of course, is to the right of 1,000, it's greater than 1,000. So 1020 could be here, or it could be here. My job now is to find out where 1020 is. There are two ways to go about doing this. The first option, I could work out where this line is. So where this critical value is, I call it C2, that's the upper bound of the accepted region. Or I could say, well, I've got the observed value of 1020. What's the chance of me getting 1020 if I know the underlying distribution? I'm going to do it that way. Let me ask this question in a more mathematical way. What's the probability that X bar is greater than 1020? So what is the probability of that? And if that probability, and if that is greater than 2.5%, then it's nothing special, so I can accept H0. But if that probability is less than 2.5%, then I think, the chances of me getting such a high mean is very, very low. It's within my critical region. Therefore, I would need to reject H naught. So this is what I need to test. Now I'm going to work out what this probability is. Again, on the H naught, just to write that again, X bar follows a normal distribution with mean 1000 and variance of 30 squared over 10, which is the same of X bar follows normal distribution with variance of 90. So how do I work out this probability? You can simply plug that into the calculator, but I'm just going to convert that into a slightly different inequality. Doesn't matter whether we use less than or equal to or less than, because this is a continuous distribution. So plugging this into our calculator, probability of X bar less than 1020 with X bar following the distribution that we have worked out is 1 minus 0.9825 equals 0.0175, which is less than 0.025, which is 2.5%. Now, because it's less than 2.5%, we know that 120 is not here. 120 is here, it's in the critical region. What's the conclusion of the test? It's always important for us to set out what the conclusion is when the question is asking us to test a certain null hypothesis. Therefore, there is enough evidence to reject H naught. It's always useful for us to say that in context of the question. The mean weight of the flower. Now, what do we say? Do we say it's less than or greater than? Because it's a two-tailed test, the conclusion that we can draw is the alternative hypothesis. The mean weight of the flower is not 1,000 grams. And that's our conclusion. Let's now look at part B. In part B, it says, Olaf decides to alter the test so that the hypotheses are H naught is mu equals 1000 and H1 is mu greater than 1000. So again, immediately you can say this is now a one-tailed test. What we can do now is to draw our distribution. Therefore, this is 5%, this is mu, and we're interested in this region here. This is the critical region now, and we don't care about what's on the left-hand side of mu. He takes the second sample of size n and finds the critical region X bar greater than C. So again, if X bar is greater than C, then we reject the null hypothesis. And we are asking the question to find an equation for C in terms of n. Let's see how we go about doing this. First of all, let's write down from our question what the null hypothesis is and what's the alternative hypothesis. H naught is mu equals 1000. H1, alternative hypothesis, mu is greater than 1000. Again, as we said before, is a one-tailed test because it's a one-sided inequality. So under H naught, X bar follows a normal distribution, again, central limit theorem with mean 1000 and variance of sigma squared over n. Here, n is not 10 anymore. N was 10 in part A, but now we are doing a second sample and we don't know the size, so we keep n as the variable. What's the definition of the critical region? The critical region in a one-tailed test of level of significance of 5% is probability of X bar greater than C equals 0.05. Let's look at our distribution together on the right-hand side. The probability of X bar, this is a distribution of X bar, probability of that greater than C. So this is where we reject H naught. To the left, we accept H naught. For any values of X bar greater than C, we're going to reject. So the probability of X bar greater than C is going to be less than 0.05. This is when we need to convert the probability distribution into a standard normal distribution. You should be very familiar with that. So minus the mean minus mu X bar minus 1000 over the standard deviation, which is the square root of the variance, which is 30 over square root of n. So we need to do that to both sides of the inequality, C minus 1000 over 30 over root n. That should equal to what we have above. Now we should be able to observe that because we've converted the normal distribution that X bar follows into standard normal distribution, this is our Z. Now we need to look at either our calculator or the statistics table to see what this value is in order for us to be able to say Okay, P of Z greater than something, let's call that A, equals 0.05. Let's see what that value is based on our tables. Looking at this table is actually quite helpful. We're interested in the 5% level of significance, and therefore the value of Z, which gives me E of Z greater than Z equals 0.05, then Z equals this number, 1.6449. That's what we're able to get from this table. Basically, we're saying if Z follows a standard normal distribution, then the probability of Z greater than 1.6449 is 0.05. And we can bring that back to our question. Therefore, A equals C minus 1000 over 30 over root n equals 1.6449, which is the statistic we get from the table. From the tables, therefore, in order for us to have C in terms of n, then we multiply 1.6449 by, what's at the bottom? Therefore, C equals 1000 plus 1.6449 times 30, which gets us to 49.347 over root n. Now, this gives us an equation for C in terms of n, which is part B of the question. Hopefully it hasn't been too bad for you so far, but let's look at part C, which might be the hardest part of this question. Part C tells us when a true value of mu is 10,020 grams, probability of making a type 2 error is 0.0050 to two significant figures. We're asked to calculate in part C the value of n and the value of C. Some of you might not know where to start, but let's write down something that we know. We need to know what the definition of type 2 error is. Let's write that down. Type 2 error is the probability of accepting H0 when H0 is false. And just for completeness, type 1 error is the probability of rejecting H0 when H0 is true. So type 1 error is an error of commission. Type 2 error is an error of omission. When we're committing type 2 errors, we're saying there's nothing to see here, H0 is fine, there's not enough evidence for us to do anything else. The error of omission, false negative. How do we convert this expression into something more mathematical? Let's have a think about what the probability of accepting H0 when H0 is false. Let's take a look at the normal distribution we had in part B. In part B, we assume that mu equals 1000. Therefore, we've got this normal distribution, mu 1000, and we've got this value of C with this 5% level of significance. That means that to the right of C, if x bar is greater than the value of C, we reject H0. And if x bar is less than C, we accept H0. The question is asking, what's the probability of us accepting H0, doing this to the left of C, when H0 is false? We know that H0 is false because we've been given mu equals 1020. Let's draw on another diagram, mu equals 1020. 1020, of course, is greater than 1000. So we've got 1000 here. I'm going to draw on the same graph the distribution with mean 1000. So I've got my critical value of C, and to the left of C is where I accept H0. So the question is effectively asking, we know that the mean is 1020. We know that this is true. And therefore, under this distribution, what's the probability that the values will be below C? The probability of the values below C is the probability of type 2 error. Importantly, we need to say that this is given mu equals 1, 0, 2, 0. Rewriting that, I'm able to say probability of x bar less than c given mu equals 10, 20 equals, what's the probability of type 2 error? We've been told in the question is 0.0050. Now, we're able to convert what's in the probability bracket into a standard normal distribution. Probability of x bar minus 10, 20 over, what is the standard deviation? Again, sigma over root n less than c minus 10, 20 over sigma over root n. That equals 0.0050. So again, this is my z. Now we're able to look at the statistics tables and then see what is this value, little z. This should be a little one. That would give me this probability. This is the same table that we were looking at before, but now we're interested in p equals 0.0050. So based on this inequality, the probability of z greater than 2.5758 equals 0.0050. This equation is simply giving me this value. So 0.005 means 0, 2.5758. But by symmetry, we're able to work out probability of z less than minus 2.5758 is also 0.005, because by symmetry again, if this is 0.005, then I know this value needs to be minus 2.5758 based on symmetry. So this is the value, minus 2.5758 is what I'm going to take back to my question. I said earlier that this value is minus 2.5758. So I'm now able to say that b minus 1020 over sigma over root n equals minus 2.5758. Again, I'm going to write down an expression of c in terms of n. So c equals, rearranging all the terms, 1020 minus 2.5758 times sigma. What sigma is 30 times 30 over root n. So that's one expression of c in terms of n. We also had another expression of c in terms of n from part B, and that was c equals, let's take a look. That was c equals 1000 plus 49.347 over root n. I'm going to use that in part C. It was 1000 plus 49.347 over root n. So now we've got two equations with two unknowns. Put that in green brackets. Two equations, two unknown. Let's just find out n first. 30 over root n equals 1000 plus 49.347 over root n. Therefore, just bringing the n terms to the right-hand side of 20 equals, working all these figures out, is 126.621 over root n. So root n is 6.33105, and is therefore 40, because n needs to be an integer. Now, with n equals 40, c is therefore 1000 plus 49 over 347 over root 40, which equals 1007.8. So these are our values of c and n. And does that make sense? Let's take a look. So we want c to be between the value of 1000 and 1020. So if c equals 1007.8, that makes sense, because below 1007.8, we are accepting h naught. We're saying that, well, it's okay, mu could be 1000, but h naught is actually false. The mu is 1020 rather than 1000. Now we've completed the hardest question of this 2022 paper. Hopefully you didn't find it too tricky, but there are a few concepts that we, of course, need to know. Central limit theorem is basic. Type 2 error is a little bit trickier, but drawing some diagrams using the stats tables actually helped us quite a lot.